not.
Okay, when we get to that point, I'll tell you.
Should we go, or?
We have to wait till 12:35.
Oh, yeah, that's right, 12:35. Sure.
Yeah, some people come in right at the last minute, and in order to be fair.
Mm-hmm. Well, I came in at exactly the last minute when I assumed it was 12:30. That was the calendar invitation, I think.
Well, that's the way the classes work around here, right? We tell people they have a class at 8:30, but it doesn't start till 8:35, and so
I wonder if we're going to have allow having students in the class in the fall. That would be really nice, because I'm teaching in the fall, and it's so much easier to teach in front of students because you get feedback, and if you see blank stares, you know you got to go back and explain. You know, you don't get that here.
Well, Mark, in Physics 1190 with 555 students, the survey at the end of the class said 70% prefer asynchronous online.
Yeah, they don't know what's good for them.
You know, and maybe that's because they would have had to be in class at 8:30 in the morning.
No, but I was thinking if I could even have 5 people in my 170 person, I'm teaching thermodynamics again, that's about 170. If I even had 5 people in the audience, I would change it to synchronous, film myself giving the class, and then post it online. And you have both. Mm-hmm. It's just the lecture style is so much easier. Anyways,
time to start.
Yeah. All right. Should I just go?
Yep.
All right. So, let's go back. I got to share that screen. All right. There we are. So this is, oh, sorry. I just want to get my laser pointer up. This is where we ended last time, right here with the electrochemistry of silicon. And so we went through this. It lithiates in a 2-phase region, and you make 15 4-phase, and that delithiates in a 2-phase region. Then you get these single-phase regions, and if you're careful in your cycling limits, your voltage limits, you can stay in the 2-phase, the single-phase regions for cycling. But if you go below 50 millivolts, you instantaneously crystallize the 15 4-phase, and it's hidden here. But you get another plateau that's identical to this one, and you're in a 2-phase region again. And this slide illustrates the problem with 2-phase region in the case of tin, because there's more 2-phase regions here. So it magnifies the problem. And that is if you have a particle and you're lithiating a particle electrochemically, of course, the lithium is coming from the surface. And so the first thing that you lithiate in a 2-phase region is the surface. And so if you're starting with pure tin, you start lithiating it, you're going to enter this 2-phase region. And so on the surface, you're going to form this phase. And you can see it formed here, and you just get more and more of it, and the tin phase is consumed at the expense of this one as you add more lithium. This phase is about 100% volume expansion compared to tin, so that causes a lot of stress, and you get cracking and fracture until you completely lithiate it. And again, things are growing here, so typically during lithiation, everything's under compression, so even though they're fracturing, they stay together. And if you lithiate more, then you enter another 2-phase region, and that makes more. This expansion of or the volume of this phase is about 100% more than this phase per host, and so you get large strain again and cracking, and the particles fracture more. And then you enter another 2-phase region, another 100% volume expansion between the phases till the whole thing's about 300% volume expansion when you get to the end of it. And by the time you get to the end of it, you're left with something that's highly fractured. And if you try to delithiate and these particles start to shrink and pull away from each other, you don't get much capacity at all. So that situation is not ideal. So one of the strategies in this field has been to make things either completely amorphous or small enough that there aren't basically enough atoms to form these big unit cells for these lithiated phases. And if you can't form the crystalline structure because you don't have enough atoms, well, you can't be in a 2-phase region. and you end up being in a single phase region. And in these single phase regions, you get a continuous lithiation of the particle. And so the particle can expand evenly. At least that's the idea. Of course, you could get composition gradients and get strain that way. But, you know, it's a lot more reversible. And then if you take lithium out and you're still in a two-phase region, then the particle can delithiate uniformly and uniformly shrink, avoiding these internal stresses and fracture. And this is illustrated here. Oh gosh, can I? Maybe if I get rid of my pointer, I can start. This is a movie by Kevin Eberman at 3M Company. And this is looking down through electrolyte at a silicon tin amorphous thin film alloy with an optical microscope. Too bad there's no scale bar. I think this is a few millimeters width here. And there's a ring lithium counter electrode around this thing as a source of lithium ions. Boy, I can just barely click on that. So now the film is expanding as it's being lithiated, it's expanding towards the microscope, and then it contracts. And this, yeah, I should pause it. So the contraction, during contraction, the film can shrink in all directions, but it's held by the substrate underneath. Still, it's pinned by the substrate. And so that's why it's cracking. It's cracking because of these mechanical interactions with the substrate and not because of two-phase regions. There's no two-phase regions here. This is lithiating and delithiating in a single-phase region. And yeah, they're pinned. These are pinned by one point, one little foot. We called it at the bottom of each one of these flakes. And after the initial cracking, then you could lithiate and delithiate these things reversibly back and forth. So you know, you can see that it lithiates again and goes back to where it was, and it's highly reversible. Of course, in a composite coating now, you've got a billion moving parts that you got to hold on to, and you can see that this would tend to disrupt any SEI layer, which is an issue in cycling. But nevertheless, that's how you get reversibility of the material itself. One thing to point out, I guess, that it's good to point out, especially in the case of silicon, often it's assumed that being amorphous means you have a single phase region, but that's not true. Amorphous materials can exist in two-phase regions with other materials too, just like the delithiation of if we go back here, when the crystalline 15-4 phase is delithiated, it forms an amorphous phase. You can have two-phase coexistence between a crystalline material and an amorphous material. So don't think that just because you're amorphous, you might be avoiding two-phase regions. It's often the case that you can lithiate a material in a single-phase region if it's amorphous, but there are rare cases that you can lithiate it and form a second phase, even if it is amorphous. So one thing to keep in mind. Here we go. So let me get my pointer back. Making things amorphous or nanocrystalline tends to make them lithiate in two-phase regions, and that reduces stress in the particle and gets you better cycling. But still, the problem, one problem with these alloys, if you make them fully amorphous, is their volume expansion is just too large. And in the case of silicon tin, again, it's about 300% volume expansion. And our experience at 3M was that if the volume expansion became larger than 150%, composite electrode coating could not tolerate it, and you get bad cycling no matter what you did. So we tried to limit the volume expansion to less than 150%, and more typically about 100% volume expansion. And at 100% volume expansion, a silicon alloy will have about double the volumetric capacity of graphite, which is about the minimum you want. That corresponds to a 15% improvement in cell energy density, and anything less than that is not really worth it. You can get 100% volume expansion even with pure silicon because if you take advantage of its unique electrochemistry. If you remember this first lithiation of crystalline silicon, here we're starting with crystalline silicon, That's a two-phase region between crystalline silicon and lithiated amorphous silicon, and it happens at 170 millivolts. So if you go along here and stop it when you get to 100% volume expansion, then you form a particle that has a core that's unlithiated silicon and the outside is lithiated amorphous silicon. And then you could do some fancy conditioning cycles that are discussed in this paper to better form this outside amorphous layer. And you get this core shell type particle. And if you stay above this 170 millivolt two-phase region voltage, you'll never lithiate the core again. And so then you cycle these tiny kinds of core shell particles, and they can cycle very well. You can kind of think of this as, we saw that sputtered film on the copper substrate. Well, now we have a film on a solid core substrate. So it's kind of the same idea. And these things, this is silicon directly from the bottle from Aldrich. And you can see if you take these are the conditioning cycles over here, 10 of them. And then after that, the voltage is limited above 170 millivolts. So you're only cycling that outer shell of silicon. And you can get very good cycling even from pure silicon out of the bottle. The problem with this is, if you're limiting the voltage up here, the average voltage is high, which reduces the energy density. And another thing is, as we'll discuss later on, to get good electrode density, you don't want porosity in your electrodes. These things have to be calendared, and to get good calendared density, you need to add graphite. And if you're adding graphite, you should cycle the graphite because you don't want it to be empty or a dead space in your electrode. And so you have to go below 170 millivolts to cycle the graphite. So this is not compatible with graphite blending, as it says on the bottom of the slide. So that was an issue with doing this kind of strategy. But especially for any time you have a material, even if you start with pure amorphous silicon, just limiting the voltage, you always end up with overall high average voltage. If you want to limit your cutoff so that you end up with 100% volume expansion, you're just cycling the top part of the silicon voltage curve. You could do much better if you add an inactive component and basically dilute the silicon such that if you fully lithiate the silicon, then this particle overall will have 100% volume expansion. Then you're using the whole voltage curve of silicon and your average voltage is lower, and that'll give you a higher energy density. So therefore, if you are cycling at a fixed volume expansion target, adding an inactive phase increases the energy density because it reduces the average voltage. And all these things that, like we saw in the previous lecture, the volume expansion is perfectly linear. You know what the average voltage is, and so you can easily model all of these things. And so you can model what the energy density would be if you had pure silicon and we're limiting the potential limit to a fixed volume expansion or a volume expansion target versus using an inactive alloy, where this is the energy density scale here, and you get a higher energy density at any volume expansion if you add an inactive component. The other interesting thing about this graph is its shape. As soon as you add silicon and have some capacity, this is the percent silicon, sorry, 12, 15% silicon, 20% silicon by volume. This is 100% silicon by volume. When you start adding active silicon to the alloy, of course, it increases the energy density a lot, and then it kind of rolls over. And where it rolls over is about 50% by volume silicon, or about 100%, 150% volume expansion, which, if you remember, was the maximum volume expansion you can tolerate in a coating. And the amount of energy density you're going to gain by having pure silicon or anything that has more volume expansion is extremely small. All the gains are made here. You can see this huge gain in energy density going up to 50% by volume silicon. After that, basically nothing. You're not gaining anything. So limiting yourself to about 100% volume expansion is exactly where you want to be. And any higher energy densities or higher capacity of your alloy is not going to help.
Mark,
Yeah.
just for the benefit of the people listening, is this curve roughly okay for a graphite silicon mixture, the black solid curve? I mean, imagine that you're adding 20 weight% silicon into graphite, and as you go along the curve, the benefits get less and less the more silicon above 50% you add to the graphite by volume. Is this basically a similar curve would be generated for a silicon graphite mixture?
This shape is similar, but of course the energy density gains are much less. Oh, wait a minute, is this? Because, let's see. Yeah, this curve was made based on a pure alloy.
Yeah.
Yeah, if you have a silicon blended with graphite, then you get a different shape. I'm going to have to look back just actually because I'm questioning myself. This could have been made for a graphite blend. It could be. No, it can't be. Yeah, 100% silicon. You can't get this if there's graphite there. You can't get over 30% improvement. It's impossible. Yeah, so this is pure silicon with no graphite. That's true. Yeah.
So I would think the shape would be similar.
It's a similar shape, yeah, for blending.
Okay.
There's a good paper from Oak Ridge National Lab that did an analysis of this. Justin Dew, a former postdoc, was a co-author on that paper. And they did that analysis with graphite.
Okay, thanks.
Yeah.
I have an additional question.
Yeah.
So you mentioned earlier that as you have more inactive phase, then you can go down lower on when you're lithiating. So if you use, say, graphite as the inactive alloy, and you don't have too much silicon, can you access the graphite capacity that way?
You're asking if you have, I'm not sure what you're asking.
So earlier, a couple of slides ago, I can't remember how many slides, you were saying, yeah, this slide, as you have less silicon and there's more inactive, to reach the 100% volume expansion, you can kind of go lower in voltage to kind of use more of the silicon, right?
Yeah.
If you have, say, graphite instead of the inactive alloy,
yeah, a lot of
you
folks
go low enough to access the graphite capacity.
Sure. I mean, this is going down to 0 volts here. If you have an inactive phase, you can go all the way to 0 volts and have 100% volume expansion. And yeah, if this phase happens to be graphite, then sure. And again, this is what Jeff mentioned in the last lecture. A strategy is to have graphite with these alloy particles encapsulated within the graphite. And then you have a completely active particle and maybe even pure silicon inside. So that's one strategy to reduce volume expansion and yet still use all active materials. Yep.
Okay, thanks.
Right. One interesting thing when you make these active and inactive alloys like this, you can also think of this as, the silicon is black here. Oh, by the way, a lot of times you see the active and inactive alloys drawn, I think even in this presentation, in the opposite sense, where the silicon are these dots surrounded by an inactive matrix. But that can't be because otherwise the lithium wouldn't be able to get to the silicon. It has to look like this. The silicon has to be a percolating phase for the lithium to get to the core. So it looks something like this. You have a silicon matrix with inactive alloy in it. But still, these inactive particles are not, or grains, they're not expanding at all, and the silicon is expanding. So you can think of it as, again, back here we had said, okay, well, this is kind of like that copper foil substrate, and you got a thin film on top. Well, now you've got a lot of substrate covered with silicon, basically. So it's kind of the same kind of idea. And there's going to be a huge amount of stress on these phase boundaries. And one way to deal with that is to make them nano, and if you do that, then you don't tend to form cracks that can propagate, and these particles tend to stay together better. And you get more homogeneous distribution of the, I guess I should say, of the strains, or the stresses, excuse me. I always get those mixed up.
Hey, Mark,
Yeah.
why do you say you have to have a percolating silicon network? Don't you just have to have a conductive matrix?
The inactive phase doesn't conduct lithium. This is for alloy materials. If you have something like SiO, then the inactive phase is an ion conductor.
Got it.
But even in so SiO, this would be a correct model. This discussion is right now restricted to alloys, where this would be sort of like maybe iron silicide, something like that.
Got it, thanks.
Yeah. So what you notice when you make these alloys is that the voltage curve of the silicon is not exactly the same anymore. It looks the same, but they can be shifted in voltage. And that seems to be because of stress potential coupling. So if you're restricting the silicon from expanding, it's going to be harder to put lithium in it. And that causes a polarization in the voltage curve. It shifts the voltage curve to lower potentials during lithiation because it's harder to expand. During contraction, during delithiation, things are more or less free to delithiate. So you don't see much of a shift during delithiation. You only see the shift during lithiation, where you get these compressive forces. And in thin films, the amount of shift as a function of the excuse me, of the stress could be measured, and it's about 100 millivolts per gigapascal of shift. And we decided to measure that as student Douglas Iaboni. This was his master's project, because we realized, well, this 15-4 phase, you form it when the potential goes below 50 millivolts. But on a thin film, you can shift the potential by more than 100 millivolts negative. That means you're shifting that 15-4 formation below 0 volts. So theoretically, you should never see it on a thin film. And that's what we found. We could turn the 15-4 transition on and off depending if the material was on a thin film. So this is pure amorphous silicon sputtered on a copper foil. And Douglas cut the foil in half, and half of it he put it in acid to dissolve the copper, and he got the flakes of silicon, and he put that in a regular coating. And you could see during lithiation, there's a little peak here, and that's the instantaneous lithiation of 15-4, or crystallization. And during delithiation, you see the big two-phase region here from the delithiation of the 15-4 phase. If he kept the amorphous silicon on the foil, then you get this black curve. And the first interesting thing is you see this big peak here. This peak is a nucleation and growth peak. So in this powder that he made by grinding up this stuff and putting it in a composite coating, you got a lot of cracks and all these uneven surfaces and points and fissures that the lithiation can start in. The lithiation has to nucleate somewhere. It has to get into the material somewhere. On a perfect, nice, smooth, sputtered film, it's very hard for the lithium to nucleate, to start to get nucleation. There's not very many nucleation sites. So you can see this initial lithiation starts here in the composite coating, but it's pushed to lower voltage. And then you get rapid nucleation because it's basically under potential lithiation now. And so this is from nucleation and growth in a thin film. The other thing you see is the voltage is shifted, just like you would expect for a thin film because of this stress voltage coupling. And you no longer see the 15-4 phase because this peak has been shifted to a potential where you never reach it. We cycled down to 5 millivolts, and this thing must have been shifted below there. We never saw it. And now you don't get 15-4 formation anymore. which is good because, again, this two-phase region you want to avoid because that's where you have these phase boundaries in your particles that there's a lot of stress and things that can cause cracking. And if you cycle a thin film and watch 15-4 growth, you can learn a lot about how these materials work. So you can see initially this is a thin film of amorphous silicon on copper foil, and its lithiation is initially at a actually it's over here at a low potential because it's stuck to the film. So this is initially you get the nucleation and growth peak here, and there's no 15-4 phase initially. And initially, this is the capacity here, and the capacity cycling is very good. And this is the area under the 15-4 peak, and initially you don't see any 15-4 peak because it's pinned to the film, and you get that stress voltage coupling. But eventually you start getting these cracks forming, as you can see in the SEM image. Where's my mouse? Not working. Ah, there we go. In this SEM image, and the edges of these flakes start to lift off. And if they're lifting off the foil, there's no more stress on them anymore by the foil, and so the voltage isn't shifted for these points in the alloy. And so you start getting some of the alloy forming 15-4. And of course, if these things are coming off the foil, that's exactly when you start getting electrical disconnection and fade. And indeed, the fade is exactly coincident with starting forming this 15-4 phase. So you can see during cycling, this is shifted to low voltage. As we cycle more, it starts to delaminate from the foil and the voltage shifts back up. And then you start to see this growth of the 15-4 phase, and coincidentally you get fade. We believe this is also the mechanism for fade in active-inactive alloys. If you start out with an alloy having a perfectly being able to lithiate and delithiate in a single phase region, we believe that's the inactive phase suppressing the 15-4 formation because of this stress voltage coupling. If you start seeing growth of the 15-4 phase during cycling of the alloy, that typically means the silicon phase is becoming disconnected from the inactive phase, and that usually means that you're going to start to see fade. So this kind of, if you have an alloy material, this kind of growth in the 15-4 phase is usually not good news. And this is exactly what this slide is talking about. Another interesting thing, if you're working on silicon, that you have to be cognizant of are the effects on the capacity of this voltage shift caused by stress potential coupling. And where this is magnified the most is in the case of nickel. Nickel especially binds well to silicon, and it's used for that reason, as a binding layer in solar panels, to the silicon solar panels. From the current collector, they put a small thin layer of nickel to bind well to the silicon, amorphous silicon layer when you're making amorphous silicon panels, solar panels. And if you use silicon, nickel and a silicon alloyed with silicon as an alloy, it especially shifts the voltage curve compared to other transition metals. Some transition metals don't shift it at all, some shift it a little bit, and nickel shifts it a lot. And it seems to be related to the binding force with silicon. And so here's the differential capacity curve of nickel with silicon with a little bit of nickel in it. It's enough to suppress the 15-4 phase completely. If you keep adding nickel, you can see the lithiation voltage is shifting, and it keeps shifting to very low potential. And that's graphed here. And there's 3 regions. In the first region, as you add nickel, nothing much is happening until you start chewing away at this peak. And you really chew away at this peak, and then this thing, well, if you start chewing away at this peak, then the corresponding peak in the charge curve is going to start to go down, and that's going to affect the average potential during delithiation. So during the initial shift, nothing much happens. You're not reducing the capacity much. You just get this stress potential coupling, which is seen during lithiation. But then you start chewing away at that first peak, and it's affecting the delithiation now. And then you get into the region where this peak is completely gone. And then you're in the valley between the two peaks, and again, nothing much happens again. So this is sort of this shape and the average potential versus nickel content is because of the shape of the differential capacity curve. Well, if you're eating away at one of these peaks in the voltage curve because of stress potential coupling, how do you know how much silicon is active in the material? And the way to determine that is by fitting the differential capacity curve as the best you can, like with Gaussian functions, and realizing that this upper potential delithiation peak is never affected. So if you calculate from this initial differential capacity, what is the fraction of the capacity in the upper potential peak, then you can track how much silicon is actually active as you add nickel. And this graph shows you what happens if you don't do that. So this is the amount of lithium per silicon as you add nickel. And you can see the amount of lithium per silicon drops off, the amount of lithium that you can put into the alloy, the lithiation capacity, basically. And it drops off quickly, and it kind of looks like, follows this dotted line like nickel silicide is being formed, which is in an inactive phase. But if you actually calculate how much silicon is there from that upper potential plateau, you find out all the silicon is actually active. And nickel is one of the few transition metals, it turns out, that the silicide is actually completely active. The two ones are copper and nickel, the most noble transition metals. The more electropositive transition metal silicides are all completely inactive. Nickel silicide is active if it's nano enough, because the kinetics are not great. But if you make something nano or amorphous, nickel silicide, all the silicon is active in it, but you don't see all the capacity from silicon because its potential is shifted to negative potentials. And so when you're looking at these materials, you really have to pay attention to the stress potential coupling to really know what's going on. So, well, this, I guess, goes for alloys. Let's see what it says here. If you want to make a good practical alloy, you should have a low volume expansion phase. Inactive phase could be a silicide or silicon oxide in the case of SiO, or lithium silicon oxide, I guess, or graphite or carbon, like was mentioned earlier. You want to limit the volume expansion by including this phase, and also you want to eliminate the formation of lithium-15 silicon 4 by the stress voltage coupling mechanism. You want to make the active phase nano to avoid grain boundaries, which you can be sources of fracture within the particle. And you want to keep the surface area small to reduce SEI formation, or I guess a better way to phrase it is keep the surface area that's exposed to the electrolyte small. So that could be made, done by, in the case of SiO, big smooth particles that have a low surface area, or by embedding the alloy within graphite so you don't have surface in contact with the electrolyte at all. So here's some examples of materials, and this is lectures from a few years ago, so the pictures are not completely up to date, and the examples aren't completely up to date. This is tin cobalt carbon alloy, which is the first commercialized alloy material, I guess. It's oh, I don't know, Jeff, this is a question for you. Was the Fuji material ever commercialized? Do you know?
Yes, there were a small run of cells that were produced. It didn't last for long.
Yeah, so that was a tin oxide material, which had a higher reversible capacity and didn't work out too well. This is tin cobalt carbon, and it was introduced by Sony, and then they took it off the market, and I don't know, it was okay. It was a very nice material, but I suppose I mean, it's really costly. You've got cobalt here and tin, which we showed is more expensive, much more expensive than silicon, and especially cobalt's expensive too. This was made by ball milling these phases together. First well, it says right here, First, they made the copper tin alloy, and then it was ball milled to disperse it in carbon to make this completely amorphous alloy. And here, the matrix phase is carbon, so that can have capacity too. And the cobalt tin phase also is active, so this is a completely active particle. And yeah, this is the reaction, and this was figured out. Well, a lot of it was figured out actually in Jeff's lab, how this is working. And the fact is that if you want to model the capacity of this, you have to assume that you're forming lithium a half carbon, which is a lot more lithium than you can put into graphite. And this is very special carbon. It's kind of mysterious too, because if you don't have this tin cobalt phase around and you just try to ball mill carbon, you're not going to get this nice capacity with low polarization. So it's still kind of mysterious to me how you can make this beautiful LiC2 carbon only when this tin cobalt phase is present. So anyways, you lithiate this material, and as with many alloys, it can phase separate during lithiation. And in this case, the tin cobalt phase separates so that you make lithium tin and cobalt metal. And then again, the carbon matrix can make LiC2. Another material that's presently commercialized is SiO. And SiO, there's a lot of models of what SiO is, and I think the leading models basically state that SiO are very nano amorphous regions of pure silicon surrounded by silicon oxide, SiO2. And here in this picture, the pure silicon is in green, and the silicon that's bonded to oxygen to form SiO2 is in blue, and the oxygen is in red. Now, according to this model, because the silicon is so tiny, even though you have regions of pure amorphous silicon, the amount of silicon on the surface of these regions is, roughly in the same order of magnitude as the amount of silicon in the bulk. And so that means you have a complete gradient of silicon compositions from pure silicon, which could be at the center of this pure silicon region, and as you go out, you get more silicon oxygen bonding. So you have, by virtue of this structure, pure silicon that might be bonded to 3 silicon and 1 oxygen, all the way up to silicon bonded to 4 oxygen in SiO2. So SiO is a distribution of silicon bonded with pure silicon all the way bonded to all oxygen around the silicon. But the basic structure is like this. When you lithiate SiO, SiO, the silicon oxide regions lithiate first because lithium more strongly bonds to oxygen than lithium, and that happens at around 0.6 to 0.7 volts, somewhere around there. You can see a little plateau in some materials where that happens, and you form a predominantly Li4SiO4, which is also a lithium ion conductor, and so that allows these completely isolated silicon regions to still get lithiated, even though they're completely isolated. And so after you make Li4SiO4, then the silicon can lithiate. And here they put lithium 4.4 silicon, but you really get lithium 15 silicon 4. And then this is reversible. For this phase, you could take the lithium out. For the Li4SiO4 phase, the lithium is basically stuck. For any commercial cell where the potential of the negative electrode doesn't generally go above a volt, you can, if you go above 1 volt, you can take the lithium out of this, but in a commercial cell, you wouldn't have the negative electrode going up that high. So this lithium essentially becomes stuck and inactive and results in a high irreversible capacity, and that the irreversible capacity can be higher than 50%. And if there's there's papers that have looked at post-mortem cycling of SiO, and it's no different than the alloy. After a lot of cycles, you can still get this surface erosion on top of the particles. The difference seems with SiO, this erosion is much slower than a typical alloy material. And it's thought that the reason it's slower is because these are large particles that have a lower surface area, where the alloys particles are sub-micron. You can see these particles are a micron or higher. So if you're dealing with sub-micron nanoparticles, this reaction tends to be a lot greater. So that's an advantage of SiO, this low surface area particles slowing down this reaction. I did say that I was going to say something interesting about SiO, which was if you calculate the volume expansion or the volumetric capacity of SiO as a function of oxygen content, you will get a very interesting result. And yeah, that might be an interesting exercise, or Jeff, I could just say what the interesting result is. Up to you.
You can say what the interesting result is.
I will say it. The volumetric capacity of Li4 SiO4 is identical almost to silicon. The molar volume per or to lithium 15 silicon 4. The molar volume per lithium is 12 for both of them. So the volumetric capacity of SiO is identical to silicon for the first lithiation at any oxygen content. It's a straight line.
It's pretty nice.
No, it's not. It's terrible. Because if you want to limit the capacity,
result is what I.
Yeah, it's an interesting result, but for practical speaking, the reason you add oxygen is to lower the volume expansion. But on the first lithiation, it doesn't lower the volume expansion compared to pure silicon at all. Has no effect. So that's a bad thing about SiO compared to, for instance, an alloy, which would limit the volume expansion because you have a completely inactive phase. So anyways, that's a good exercise to do. And calculating volume expansion at SiO is interesting because you cannot use those formulas that I had before. You have to say, oh, I didn't write it down. I should have written, it would be nice if I have a succinct formula here, but basically the lithiation reaction is lithium plus silicon or plus SiO gives you Li4 SiO4 plus lithium 15 silicon 4. And you have to use those reaction products to calculate what the volume expansion is that way, because what you're forming is not an alloy. This is now a compound, a new compound. And so you can't use those equations that we had for pure alloys before.
So Mark, the first time you cycle, you lithiate this composite, you get what sort of volume expansion? It depends which voltage you go to, but typically.
Well, I mean, like I said, it will expand exactly the same as pure lithium. So it'll be
versus silicon.
Versus silicon, yeah. So that was 280%. So this will be about the same, irregardless of oxygen content.
Got it.
Where again, so let me go back here because I think it's interesting too. Where did we have that? Oh, I didn't have that. Okay, never mind. I thought I had a graph of percent volume expansion versus how much alloy you have in there. But anyways, with an alloy, the percent volume expansion obviously goes down if you add the inactive phase, and as you add oxygen, the volume expansion doesn't do anything for this one. Just stays at 280%. And this is where we were. Okay, this is, again, an older presentation. Back when this presentation was made, 3M had a commercially available alloy. It was 3M, oh gosh, I don't know. They had V6, V7, V8, all the way up to V12 alloy. And they're all silicon iron-based alloys. And again, oh, this is an inverted slide. Yeah, you can see I put this slide together in the inverse way, which is incorrect. If the 3M alloy did look like this, then the lithium would never be able to reach the silicon phase because the alloy is completely inactive towards lithium. So this is an inverted drawing, not a good drawing. But with an alloy, you don't have this SiO issue of having an irreversible consumption of lithium. And so the irreversible capacity can be small. I think the lowest they achieved was something like 15% irreversible capacity, as opposed to 50% for SiO 1-to-1 theoretically. And you can restrict the volume expansion too, because you're diluting the silicon. And you don't have any 15.4 plateau because of this stress voltage coupling in the particle. Okay, and I think this is coming to the last point here, which is trying to make a coating with alloy materials. And if you coat in the lab, if you coat anything by hand in a hand coating and you measure the porosity, it's about 60% any particles coated by hand. Maybe graphite, no, those are 60% too. They tend to be roundish. If you want to get lower porosity, you have to calender. And for alloy materials, it's very difficult to get this porosity out. If you calender an alloy, they're irregularly shaped particles and they can't slide against each other. And the only way to get the porosity lower is when you calender it, you have to calender it under high pressure enough to break the particles and cause fracture. And then you can start lowering the porosity. In a lithium cell, those kinds of pressures are never reached. So when this thing expands, it expands basically unrestricted. The separator will crush, the current collector will tear, the whole cell can will bulge before any compaction or lowering of porosity will occur. And so basically what happens is all these particles expand at the same time, and the pores in between them expand too. It's just like taking this thing with a mouse and expanding the whole thing, and you get something that looks like this. That's still 60% porosity. And so after all your work in making something that can store a lot more lithium, you've got mostly empty space in your coating, and your energy density will be less than graphite. And that's why you have to add a graphite, so you can calender these things and get the porosity down. The other problem with calendering them, if you do calender them, if you remember, these things only cycle well if they have a binder that coats all the surfaces, which again is mysterious, but that's true. And if you're calendering them enough to fracture them to reduce the porosity, as you can see here, this is pre-calendered, you can see all the porosity in here, and this is densified somewhat by calendering, by fracturing the particles. And you can see by eye, these are the same coating before and after calendering. The particle size has gone down a lot. And of course, if you're fracturing the particles, now you have particles that have no binder on them or some fresh exposed surfaces with no binder. And the cycling is terrible. So this is before you calender it, you got half decent cycling. And after you calender it, the cycling is very poor. So to try to improve that, you add graphite, which is a calendering lubricant. And you can, some commercial cells, you can even find graphite in the positive electrode because it can help densify the coating. And that graphite can help the particles slide by one another. And so you can, this is, again, before calendering and after calendering. And if you add enough graphite, you can still see some big rocks, some big particles that haven't broken because the particles were able to move around. There was enough graphite in there. The more homogeneous, yeah.
Oh, can I ask a question about the equation you had, I think, 2 slides before, the particle expansion and porosity expansion? I didn't quite get the correlation here, why the coating expansion would be the same, then the same number value. Maybe you can explain
because
that.
as the particles expand, like I said, they do not densify. The whole thing is expanding. So it would be like if I wonder if I could do it. I'll do it I'll do right here. This is how they expand, like that.
All right.
You see what I mean? It's like taking my mouse and just expanding the whole thing. The particles expand, the porosity expand by exactly the same thing. They're not densifying. So that means,
okay.
or the porosity. So the percent porosity remains unchanged no matter how much I can move my mouse like this.
Well,
So
the current
in general-
collector doesn't get longer. That's why they're stacked on top of each other on the right-hand side.
Yeah, on the right-hand side, they have to stack, and actually this is probably incorrect because they de-densify. They tend to decalendar as they expand and contract because they move around and they're not going to compress themselves together. They tend to unpack, and so
Even worse.
it's even worse. Yeah.
I always have a little bit of trouble imagining what external compression would do on such an electrode. Would it just reduce the porosity expansion then, and we would still have alloy expansion?
It tends to improve cycling a bit because of improving electrical contact. But like I said, we're talking about so this calendaring to reduce the porosity is gigapascal force. You can calendar the nip pressure, and it's gigapascals. You're never going to reach that in a, megapascals, which is still ridiculously high. You won't reach that in a cell. Separator is going to crush before you do this, right? So this is orders of magnitude higher pressure than typically what's in the cell, which is 15 to 20 psi, maybe 40 psi stack pressure, something like that. It's not even close. So this thing would crush the separator without even knowing it was there.
Okay. Thanks.
Yeah.
I have a question here as well. Would the situation change if we had a bimodal distribution of particles? So if we had smaller particles that go into the pores of those bigger ones?
Oh yeah, I mean you can improve coating porosity or reduce coating porosity by different particle size distribution. That's true, but you can never get down to what you need for a coating, which would be 15 to 20% porosity. That kind of level you can't get by just coating without applying any pressure on the top. Unless you have particles maybe, well, I don't know if you can or not. Maybe graphite that are flakes might be able to do that. But in our experience, you can see that this distribution is huge on the left, right? This is a huge particle distribution. I don't know if I don't have my pointer up. This is about as bimodal as you can get, and this is 60% porosity. In our experience, we've never been able to achieve high porosity without calendaring.
I see. Okay, thank you.
And I guess it's kind of like trying to make a brick wall that's where the bricks are nicely stacked by throwing the bricks into a pile. You're never going to do it, no matter what the bricks are particle or size distribution is. They're never going to come together and form this kind of interlocking kind of pattern. Yeah, you can see how nicely the particles fit together when they're calendared. You can't do that without pressure. And if you add graphite, the particles don't break anymore, and you see that in the cycling. And I guess, I mean, I don't have to go into that more. We're kind of running out of slides. I think that's the main point. And this is an 1860 cell that 3M made by putting everything together. They have their alloy, they blend it with graphite, they can calender it to high density and get good cycling. So here's 500 cycles from an alloy in an 650 cell. It's only 2 milliamp hour cell, or 2 amp hour cell, I should say. This is, yeah, it shouldn't be milliamp hours per gram. It should be milliamp hours for this cell.
Yeah, and the interpretation of this capacity fade here is it's virtually all from lithium inventory loss on the negative electrode.
That's right.
Continually growing SEI.
That's right. And
what it means is the mechanical properties of the negative electrode are good. But
that also means
SEI growth is out of control.
Yeah, and if you try to take apart the cell after this, you'll find everything's tightly packed because the negative electrode has been continuously expanding through this whole time because the SEI has been accumulating there, which has a low density. Okay, so that's about it then. So this is, yeah, back then I wrote a bunch of topics not mentioned and probably more now, but actually this is not too bad, I think. Yeah, so the chemistry of silicon with these phases, tin alloys weren't mentioned in this talk much, although Nexelian alloy was mentioned a bit. Silicon carbon composites were important then, and they were mentioned now, they're still important. How you make these things, how you design the particles themselves. Cell design, there's a big, that's a big topic. How you match this with a cathode. The cycling of the anode depends on the cathode chemistry. How you tolerate the volume expansion in the coating and in the cell. And as Jeff mentioned, the last point is the SEI formation and growth and how you can hopefully reduce or eliminate that. So let's see what I said 3 years ago. Yeah, so you can get these things to work half decently, but you have to bring in together, you know, the fundamental understanding of silicon electrochemistry. That had to come first, and then particle design to make the particles work. How to make the particle, you know, what's the interaction between the active phase and the matrix phase, whatever, you know, if it's silicon alloy or silicon SiO, you have this the stress voltage coupling and other effects that can change the voltage curve, binder chemistry, design of the electrode, the electrolyte formulation and additives we talked about, and it's a whole package really, the whole cell from the particles all the way up to the cell design, all have to be custom made around any electrode, and that's really really true for alloys. And 3 years ago, there was a lot to learn, and there's a lot more to learn. As we go ahead, we found out there's more things we didn't consider, and more capability we have in making fancy particles that maybe can work better. And the main challenge is still increasing cycle life in these materials so they can be used in practical cells. All right, it looks like we're pretty much on time.
Okay, thanks, Mark. I think if people have questions, this is your chance because Mark won't be back.
I have a question about something that wasn't mentioned, the balancing with the cathodes. So what's the lowest irreversible capacity you can get with commercial silicon electrodes at the moment, and how to counter that?
Well, it's a play on how much you blend with graphite. So your irreversible capacity, I mean, if you're blending 5% SiO with graphite, it's not going to affect all that much. If you know, you can buy SiO that have maybe less than 30% irreversible capacity, and then you're only putting 5% maybe as a reservoir and with the graphite, and really you don't see a huge impact. If you want to start cycling the alloy and getting capacity from the alloy and increasing the alloy, then you have to start dealing with irreversible capacity. If you use SiO, if you use silicon alloys that don't have that problem, then it's not much of a problem at all. It depends what kind of alloy you use and how much you want to use the alloy. Is there a more specific question, or?
Are you aware of any alloys, you know, like silicon metal that are commercially available? I mean, SiO is commercially available.
Okay.
Silicon carbon nanocomposites are available.
Yeah,
Silicon
there's
is
lots.
available. Nanosilicon is available.
Yeah. You mean it's silicon metal alloys?
Yeah, like silicon and iron carbon or things like that. Or anything like that commercially available at this time?
Not after 3M. I'm not aware of anything. I know, who was it? It was Johnson Matthey that took over the 3M patents. Maybe they're going to have something if it was worthwhile to them. Maybe. Yeah.
Maybe, so at the moment, really, there's nothing in the alloy space that everyone thinks of an alloy as silicon with a metal.
No, there isn't. But I think there could be. I think that these things have a lot of promise. I think you can make them just as good as SiO, but not have the problems of SiO. I don't think there's any fundamental reason why you could not do that. And like I said, SiO is nice, and I think the fundamental reason why SiO is nice is because the surface area is low. Other than that, it's all disadvantaged.
Well, SiO doesn't crack, right?
Well, the alloys don't crack either.
If that's the case, then the alloys are good.
Yeah, I mean, it's the same mechanism that you see after cycling when you do a cross section. You see for the alloys in SiO, this is exactly the same cracking fracture that goes from the surface in. The core of the alloy during cycling is fine. Where it's in contact with the electrolyte, this is where you see the problem, and it's the same as SiO. But maybe SiO somehow this reaction is slowed. It could be. It could be actually slowed, but nobody has ever had a good study of comparing the reaction rate of the surface reaction.
Isn't that as simple as just high precision coulometry of coulombic efficiency of electrodes that don't lose capacity?
Yeah, and I guess to do the measurement, you first grind down the SiO so it's the same size as the alloy.
Or you'd make big alloy, one or the other.
Well, which one is easier to do? Grinding.
Yeah.
Right? Any other questions?
I have a question about the SEI. I'm not an electrolyte person, so sorry if this is a silly question. But does the SEI that's formed on these silicon and silicon alloys, is that different from SEI that's formed on graphite? Or does it just depend on, like, for example, because the silicon has surface groups like silicon hydroxides and things like that, do those participate in these reactions? Or is it just a function of the electrolyte composition in the surface area?
I don't think anybody can answer your question. And the reason I don't think anybody can answer your question is, I'll go back down here. Whenever you see papers about what is the composition of SCI, they always include species that are the same for graphite, lithium carbonate. If you have FeC, there's lithium fluoride and things like that. But studies of the surface of the SCI in silicon also include species that include silicon. And the reason I think, is because the surface is fracturing. And how are you going to study this thing and figure out, is there any silicon in the SEI or not? The silicon is fracturing into such nano domains. Is there silicon in the SEI or is there not? I don't know. So that's the only difference that comes to my mind. I mean, all the other components, there are polymeric components, and these things depend on the additives that you have in the electrolyte, and it's the same as graphite, except in case of silicon, there's more of them, of course. But is there silicon in the SEI of silicon, or is there not? I don't know.
Okay,
What do
thank you.
Do you have any comment about that, Jeff?
I remember seeing people, saying there's silicon containing things in the SEI, but it's difficult, I would say, to be sure, like you say. Any measurement tool that you would use is going to probe deeper than the very surface.
Well, look at the bottom panel here, pure silicon.
I know.
It's all SEI.
I know.
Yeah. Okay, well. Any more questions? Going once, twice?
Quick one. One
All right. Go
about
ahead, Ron.
so what's the highest practical silicon loading that's possible at the moment in a commercial zone?
Well, that depends on exactly this here. How much graphite do you need to add to obtain a high density coating that can cycle well? And this is unfortunately a weight percent, but this was 3M alloy. What was the density? It was around it was around 3, I think, something like that. Anyways, you could have 60% by weight alloy and 28% by weight, or 60-28 fraction by weight, and still get good cycling. If you put less graphite in and tried to calendar it, that's when you started to get this problem of there's not enough graphite as a calendaring lubricant. So the maximum amount of graphite we found was, or the minimum amount of graphite and the maximum amount of alloy was governed by how much graphite you need to obtain a high density coating.
Okay, thank you.
Which means that you can have more alloy than graphite, and get good, get good cycling of the coating.
Okay, I think this is a good place to call it a day, but I would like the people that are registered in the class that have done homework 8 to just hang around. I just want to talk about one problem on homework 8 for a minute. So thank you very much, Mark.
All right, thank you. See you later.
And others can leave that aren't in the class if they want to, or if they want to hear the story, they won't know what I'm talking about, they're welcome to stay as well. I don't know why anyone would want to know that. Yeah, so I want to talk about the problem on homework 8 that involved the patent by this Fujimoto guy. So there's a story behind this, and then we'll get to the patent. So I remembered this patent because I looked at it. And then a few years later, I was asked to be an expert witness in a patent lawsuit between BYD and Sanyo. Sanyo was saying BYD is using graphites that we have patented. Sanyo has patented. And they put a patent, they showed the patent that BYD was infringing. So I was asked to consider this patent and figure out if BYD was infringing. So I looked at this patent. It was by this guy named Fujimoto, same guy. And you know that we understand a lot about making carbons. You learned about that in the beginning of this class. Well, there were carbons in there in this patent that were impossible to make. Things like a D spacing of 3.35 and a number of parallel stacked layers of only 2. You can't make a carbon like that. It's impossible. Because if you only have 2 stacked layers, the D spacing is bigger. And it went on and on. There were a gazillion types of carbon in this patent that were just impossible to make. And they had theoretical capacities that were, greater than numbers that were possible for carbons like this. So I got incredibly suspicious of this patent and said, it's impossible. There's got to be fraudulent data here. And at that moment, it triggered in my brain this patent that I asked you guys to read. And I was meeting with these patent lawyers here at the building, and I ran to my office and I found this patent that I gave to you guys to read. And it's the same guy, this Fujimoto guy. And the patent that I asked you to read is a complete fabrication, because you cannot intercalate most of these divalent atoms and none of the trivalent atoms into graphite at all. And if you look at the voltage curves of the intercalation of the divalent atoms into graphite, the capacities are exactly double that of lithium, because you get 2 electrons per intercalant instead of 1 that you would get for lithium. And if you look at the trivalent data for the trivalent systems, the capacities of the full cells are exactly 3 times, because you get 3 electrons. The patent is a complete fabrication. And if you look at the voltage curves, it looks like they're drawn with a pencil. They're absolutely flat. There's no features. There's nothing. All these fancy positive electrodes, materials that you never heard of. Do you think none of them would ever have a sloping voltage curve? you get a sloping voltage curve in a full cell. So I gave you guys that thing just to see what you would think of it. Did anyone think it was a total fabrication?
Yeah, I was skeptical about the voltage curve as well. I was like, this looks too nice and it's too flat, and yeah, but I never thought it would be fraudulent, I guess.
Yeah, I don't
Is
know
there
how.
a reason why he gets away with that? Because now you have two already that like he's done.
Well, I don't know if I told you guys this story or not, but I was talking to a guy named Tokiyushi Noma, also from Sanyo. He might be on one of these patents, actually. And I had met him when I was working at Mali Energy, and I think he is maybe on one of these patents. Anyway, I emailed him about this, and he said, Dr. Don, you have to realize that a scientific and a publication and a patent are totally different. And in Japan, these researchers they have patent quotas that they have to meet. You know, they have to have whatever it may be, 1 patent per month filed, or they're, you know, asked to slit their throats. And so they're under pressure to file patents. And anyway, this is just complete fabrication. It's incredible.
Well, I guess they're the
Incredible.
ones that are paying the tens of thousands of dollars for it. So
It's quite hilarious. Anyway, I thought you guys might enjoy that. I hope you didn't struggle over it for hours and hours and, you know, drive you crazy. But
Thanks,
it
sir.
is good that Saad at least thought, hey, there's something fishy going on here. Okay, any comments? All right, that's all for today. So we'll finish on Wednesday. I'm pretty sure we'll get through what I have on Wednesday. I emailed you the notes already. All right, goodbye.
have a good day.
Thank you.
Right.